The engineer rebuilt a Tiger tank's transmission and unlocked a speed no German manual listed June 12, 1944. The vehicle testing establishment, Chobham, Surrey, England. Alan Morrison's hands are black with transmission fluid. The Maybach HL 230 P45 engine roars at 3,000 RPM behind him, drowning out the shouts from the observation bunker. He's lying on his back beneath 56 tons of German steel. Tiger 131, the only running Panzerkampfwagen 6 captured intact on the Western Front. The gearbox howls like a dying animal. Something in the pre-selector mechanism is grinding, metal on metal, the sound that's haunted him for 3 weeks. "Morrison, shut it down!" Major Collins' voice cuts through the noise. He ignores it. His left hand finds the adjustment rod. Quarter turn clockwise. The grinding intensifies. Half turn back. Still wrong. The Tiger's been stuck at 23 miles per hour maximum. Pathetically slow for a machine that German intelligence claims can hit 28. But Morrison heard something 3 days ago during a cold start test. A harmonic in the transmission, barely perceptible, that shouldn't exist if the German technical manual is correct. Three-quarter turn click, the grinding stops. The howl becomes a purr. He slides out from under the tank, face streaked with grease, and looks up at Collins. Third gear synchro was backwards. Someone at Henschel installed it reversed. That's impossible. This tank came from the factory. Get in. 10 minutes later, Tiger 131 accelerates down the Chobham test track at 38 miles per hour. 10 miles faster than any Allied intelligence report claimed possible. 10 miles faster than any captured German manual specified. Fast enough to rewrite every tactical assumption about Tiger engagements. Fast enough to mean the difference between a panzer division reaching defensive positions or being caught on the march. Fast enough to have changed battles already fought. Spring 1944. Allied forces are preparing for D-Day, and military intelligence has a Tiger problem. Since Tunisia in 1942, the Tiger Y has been a terror weapon. Its 88mm KWK-36 gun can penetrate any Allied tank from 2,000 yards. Its frontal armor, 110mm thick, is effectively invulnerable to the American 75 and British 6-pounder at combat ranges. In Normandy's close terrain, in the Bocage country where engagement ranges shrink to hundreds of yards instead of thousands, the Tiger will be devastating. But intelligence knows one crucial limitation: speed, or rather lack of it. The Tiger's official maximum speed is 28 miles per hour on roads, according to captured German technical documents. In practice, British and American intelligence analysts believe the real number is lower, perhaps 23 to 25 mph based on battlefield observations and interrogations of captured crews. This matters because tactics depend on it. If Tigers are slow, Allied forces can use mobility as an advantage. Sherman tanks can't penetrate Tiger armor frontally, but they're faster. 30 mph road speed. The doctrine is simple. Flank, maneuver, use speed to avoid the 88's killing zone. Get around to the Tiger's thinner side armor. Don't engage frontally. Don't play the Tiger's game. Except the doctrine is built on faulty data. In May 1944, the War Office's Department of Tank Design receives a disturbing report from the Soviet front. A captured Tiger I, tested at a facility near Kubinka, achieved 32 miles per hour during trials, significantly faster than British or American intelligence estimates. The Soviets attribute this to proper maintenance procedures not observed in field conditions. But the discrepancy nags at someone in London, someone who flags the report and sends it to Chobham. The vehicle testing establishment at Chobham exists to answer questions like this. Since 1938, it's been the British Army's primary facility for evaluating military vehicles, friendly and enemy. In a sprawling complex of test tracks, workshops and firing ranges spread across Surrey countryside, engineers systematically dismantle, analyze and test every captured enemy vehicle they can acquire. Their Tiger collection is limited but growing. Tiger 131, captured in Tunisia in April 1943 after taking a hit that jammed its turret, is their prize specimen. It's the only running Tiger in Allied hands. For a year, they've been testing it, measuring everything: armor thickness, gun performance, fuel consumption, mobility. The speed tests have been frustrating. Maximum speed achieved, 23.4 mph on concrete roadway. Transmission temperature 95 degrees C, reads the March 1944 test report. Vehicle exhibits significant vibration above 20 mph, gear shifting difficult. Driver reports heavy steering effort. Conclude, vehicle mobility significantly inferior to Sherman M4, 30 mph, and Cromwell, 38 mph. Tactical advantage. Allied forces maintain mobility superiority. The conclusion goes into briefing documents. It informs tactical planning. Thousands of Allied tankers prepare for Normandy believing they're faster than Tigers. But Lieutenant Colonel Alan Baxter, commanding officer at Chobham, isn't satisfied. The Soviet report bothers him. More importantly, something else bothers him. The Tiger's reputation. German crews call the Tiger unstoppable. They don't act like men driving slow vehicles. In February 1944 at Anzio, Tigers broke through Allied lines with what American after-action reports describe as surprising speed. In March, during the Hungarian offensive, German panzer divisions covered ground faster than intelligence predicted. At Normandy, when D-Day comes, the 12th SS Panzer Division will reach the front from Caen in hours, not days. These aren't the movement rates of 23 MF tanks. Something's wrong with 131, Baxter tells his chief engineer in early May. Either it's damaged in ways we don't understand, or we're doing something wrong, or the Germans are lying in their manuals. Find out which. The chief engineer assigns the problem to Alan Morrison. Alan Morrison isn't a tank expert. He's 34 years old, a civilian contractor, and until 1942, he designed industrial mining equipment for a firm in Yorkshire. He knows nothing about military vehicles, military doctrine, or military anything. What he knows is transmissions. Born in 1910 in Barnsley, Morrison grew up in Yorkshire coal country. His father was a mine engineer, his grandfather a pit foreman. He learned machinery the way some children learn languages, by immersion, necessity, and obsession. At 16, he was rebuilding hauling equipment in the Warncliffe Woodmore pit. At 20, he held 2 patents for improvements to underground conveyor systems. His expertise is obscure but deep, pre-selector gearboxes for heavy machinery operating under extreme load conditions. It's a niche within a niche. Pre-selector gearboxes, where the next gear is selected in advance and engagement happens via a separate control, are complex, temperamental, and brilliant when properly designed. They allow smooth gear changes under full load, critical for machines that can't pause operations. Morrison's particular genius is diagnosis. Give him a malfunctioning transmission and he can hear what's wrong. Not metaphorically, literally hear it. Harmonics, vibration frequencies, the specific pitch of grinding metal. He's that kind of engineer, the kind with an almost supernatural feel for machinery. When war comes, his firm shifts to military production. Morrison expects to design tank transmissions. Instead, bureaucracy assigns him to aircraft engine testing at a facility in Derby. It's important work, but wrong for his skills. He spends 2 years being underutilized, growing frustrated, submitting transfer requests that disappear into the War Office bureaucracy. In March 1944, someone finally reads one of those requests. Someone who knows Chobham has a Tiger problem and remembers Morrison's pre-selector expertise. The Maybach HL230 engine in the Tiger uses a sophisticated pre-selector gearbox, 8 forward speeds, 4 reverse epicyclic steering mechanism. It's exactly Morrison's specialty. The transfer comes through on April 3rd. Morrison arrives at Chobham on April 10th, walks into the testing facility, and sees Tiger 131 for the first time. "She's beautiful," he says. The technicians think he's joking. He's not. For 2 weeks, Morrison just observes. He watches test runs. He listens to the engine, the transmission, the final drives. He reviews every technical document. German manuals captured with the tank, British intelligence translations, Soviet test reports, American analyses. He reads maintenance logs, failure reports, parts inventories. He's looking for something that's not in the documents. Something the Germans wouldn't write down because it's obvious to them. Something the Allied engineers missed because they're not listening correctly. On April 28th, he requests permission to conduct a full transmission teardown. "We've already done that," the senior technician tells him. "Twice, everything's by the manual. It's just German engineering. Overcomplex, temperamental. Then let me do it a 3rd time." They give him 3 days and a team of 2 mechanics. Morrison strips the Maybach transmission to its component parts, laying everything out in sequence on the workshop floor. Pre-selector mechanism, epicyclic gears, steering clutches, final drives. 700 components, each one cleaned, measured, documented. He finds nothing wrong. Everything matches the German technical specifications. Every clearance is within tolerance. Every gear shows normal wear patterns. The transmission is correctly assembled according to the manual, but it's still wrong. He knows it's wrong because he can hear it. May 15, 1944. Morrison requests permission to run Tiger 131 with him inside the hull, near the transmission. That's not standard procedure, Baxter says. I need to hear the transmission under load. Not from outside, inside. It's 140 degrees Fahrenheit in there when the engine's running. Noise levels are dangerous. I'll wear hearing protection. They give him 20 minutes. Morrison climbs through the belly hatch into the Tiger's fighting compartment, then squeezes past the turret basket into the engine bay. The space is cramped. German engineers designed it for maintenance access, not comfort. He wedges himself between the engine block and the transmission housing, positions a mechanic's stethoscope against the gearbox casing, and gives the signal. The Maybach roars to life. Heat hits him immediately, a wall of it from the engine. The noise is overwhelming even through hearing protection, a metallic cacophony of pistons, gears, explosions. The entire hull vibrates. But Morrison isn't listening to the engine. He's listening to the transmission. First gear. The Tiger moves forward. Normal engagement sound. Clean. Second gear. The pre-selector engages. Still clean. Maybe a slight harmonic, barely noticeable. Third gear. There it is. A whine that shouldn't exist. High frequency, almost ultrasonic. It appears for maybe half a second during the shift, then vanishes. But it's there. Fourth gear. Nothing unusual. Fifth gear. Nothing. He signals for reverse. First reverse gear, normal. Second reverse gear. There's that whine again, same frequency. Third reverse, nothing. Fourth reverse, the whine returns, stronger this time. Morrison signals to stop. He emerges from the hull 15 minutes later, soaked in sweat, partially deaf, grinning. The odd-numbered gears have a phase shift harmonic in the synchronization. It's barely detectable because it only occurs during engagement, maybe 400 milliseconds. But it's there. What does that mean? Baxter asks. It means the pre-selected timing is off. Not by much, maybe 50 milliseconds, but enough to create friction during engagement. That friction is robbing power and speed. The manual says the timing is correct. Then the manual is wrong. Or our assembly is wrong, or something about this specific tank is different from the specifications. Morrison spends the next week with the German technical manual, trying to understand pre-selector timing theory. The document is comprehensive but not complete. It's a maintenance manual, not an engineering design document. It tells you how to maintain the transmission, not why it's designed the way it is. The timing specifications are clear. The pre-selector should engage 62 milliseconds before the main clutch disengages. This allows the next gear to be ready when power shifts, creating smooth changes. The manual provides the adjustment procedure, a series of measurements and settings that supposedly guarantee correct timing. Morrison follows the procedure exactly. He measures everything twice. The timing is set to 62 milliseconds, exactly as specified. But the harmonic is still there. On May 28th, he has an idea. Instead of measuring the timing statically, with the transmission disassembled, he'll measure it dynamically while the tank is running. He fabricates a simple measuring device, a contact switch attached to the pre-selector arm wired to an oscilloscope. When the pre-selector engages, the switch closes, creating a signal on the oscilloscope. By comparing this to the engine RPM signal, he can measure the actual engagement timing under load. The test takes 3 hours. Morrison runs Tiger 131 through every gear combination, recording oscilloscope traces. When he analyzes the data that night, he finds something extraordinary. The pre-selector timing isn't 62 milliseconds. It's 112 milliseconds, almost twice the specified value, and it varies by gear. Third gear is 127 milliseconds. Fifth gear is 98 milliseconds. The timing is all over the place, but always longer than the manual specifies. Longer engagement time means more friction. More friction means more wear, more heat, more power loss. The Tiger is fighting itself every time it shifts gears, but why? If Morrison assembled the transmission exactly to specifications, why is the timing wrong? He tears down the transmission again. This time he's not looking for damage or wear. He's looking for something specific, the pre-selector engagement mechanism itself. It's a complex assembly of springs, pawls, and cams that control when the selector arm moves. Morrison measures every component against the German specifications. Everything is correct. Spring constants, cam profiles, clearances, all within tolerance. The mechanism should produce 62 millisecond timing, but it doesn't. June 3rd. Morrison is lying awake at 2 a.m. thinking about the problem. The German manual specifies 62 milliseconds. His measurements show 112 milliseconds. The mechanism is assembled correctly. Therefore, he sits up in bed. The Germans aren't wrong. The manual isn't wrong. The assembly isn't wrong. The assumption is wrong. Everyone, including Morrison until this moment, has assumed the manual describes the Tiger they have. Tiger 131, captured in Tunisia in April 1943. But what if 131 was built differently? What if early production Tigers used different specifications? What if the manual they have is for later models? The next morning, Morrison requests every document related to Tiger 131's capture and identification. The tank was knocked out by a British Churchill tank, 6-pounder hit to the turret ring. It jammed the turret but didn't penetrate the hull. German crew abandoned it. British forces recovered it quickly, before German engineers could destroy it. The chassis number is 2531. In the German numbering system, that's the 31st Tiger produced by Henschel, one of the first 35 Tigers ever made, built in summer 1942. Morrison requests every German document Chobham has about Tiger production changes. The files are incomplete. Captured documents, intelligence reports, technical bulletins. But there's enough. In October 1942, Henschel modified the pre-selector mechanism to address excessive wear in high-load conditions. The modification changed spring rates and cam profiles, which would change engagement timing. Tiger 131 was built before that modification. The manual they have is for post-October 1942 production. Morrison has been assembling an August 1942 transmission using October 1942 specifications. He tears down the transmission one more time. Now he's looking for pre-modification components. He finds them. 3 springs with different wire diameters than specified, cams with subtly different profiles. Original components from August 1942 installed at the Henschel factory. The question is, what were the original specifications? The modification bulletin doesn't say, it only describes the changes, not the baseline. Morrison has to reverse engineer the specifications from the physical components. It takes 2 days. He measures spring constants, calculates cam acceleration profiles, models the kinematics. By June 8th, he has a theory. The original timing was 98 milliseconds, not 62. The Germans shortened it in October 1942 to improve performance. But someone at Henschel, maybe during a field repair, maybe during factory maintenance, replaced some of 131's original components with later spec parts. Not all of them, just some. Enough to create a mismatch. The transmission is a hybrid. August 1942 components mixed with October 1942 components, creating timing inconsistencies that appear as harmonics under load. Morrison fabricates new components to match the original August 1942 specifications. Custom springs wound to the correct constant. Cams machined to the original profiles. By June 11th, he has a complete set of pre-modification parts. He assembles the transmission one final time. June 12, 1944. 14:30 hours. Tiger 131 sits at the start of the Chobham main test track, 2 miles of concrete roadway designed for high-speed vehicle testing. Major Collins is skeptical. "You're telling me you've made the tank slower?" "No," Morrison says. "I'm telling you I've made it consistent. The German manual was optimizing for later tanks. This tank was built to different specifications. I've restored those specifications. And you think it'll be faster?" "I think it won't be fighting itself anymore. Baxter is more interested in the implications. If you're right about the production changes, how many early Tigers are still in service?" Morrison shrugs. The Germans started mass production in late 1942. They'd built maybe 100 Tigers before the October modification. Some were lost in combat. Some probably got rebuilt with later parts. But there could be 30 or 40 still running with original transmissions. And they're all faster than we think? If they're properly maintained, yes. The test protocol is straightforward. Maximum acceleration from standstill to top speed, holding top speed for 1 mile, then emergency braking. Standard procedure. They've done it 20 times with 131. The previous record is 23.41 per 8. Morrison sits in the hull again, this time positioned to watch the transmission under load. He's wearing hearing protection and has a kill switch. If anything goes wrong, he can shut down the engine immediately. The driver is Corporal James Wheeler, an experienced test driver who's run 131 more than anyone. He knows the Tiger's quirks, its tendencies, its limitations. "Ready," Wheeler says over the intercom. Morrison gives thumbs up. The Maybach engine idles at 1,500 RPM. Wheeler engages first gear. The Tiger lurches forward, 56 tons of steel accelerating with surprising quickness. First gear is always good, short, powerful, designed for the Tiger's massive weight. Shift to second. Morrison watches the preselector. It engages smoothly. No grinding, no harmonic whine, just clean mechanical engagement. The Tiger accelerates harder. Third gear, Wheeler makes the shift. Morrison hears it. Perfect. The harmonic is gone. The transmission sounds completely different now, purposeful instead of strained. The Tiger is building speed faster than Morrison has ever felt. Fourth gear, still accelerating. The speedometer, a German instrument calibrated in kilometers per hour, sweeps past 30, 35, 40. That's 25 mph, faster than they've ever achieved in third gear. Fifth gear. Wheeler makes the shift at 45 km/h. The Tiger is flying now, engine roaring at 2,800 RPM, every gear doing exactly what it should. 50 km/h, 55, 60. Morrison checks the transmission temperature. 70.8 to go, well within normal range. It's barely working. The power that was being wasted in friction is now going to the tracks. The speedometer hits 62 km/h and holds. Wheeler calls over the intercom. "She's still pulling. I can give her more." "Do it," Baxter says from the observation bunker. Wheeler increases throttle to maximum, 3,000 RPM. The Maybach is screaming. The speedometer climbs. 63, 64, 65. At 65 km/h, just over 40 mph, Morrison feels a new vibration starting, not from the transmission, from the suspension. The Tiger is hitting its mechanical limit, not power, but the ability of its interleaved road wheels to handle the speed. The vibration is tolerable but increasing. "That's the limit," Morrison says. "Back it down to 60. Wheeler reduces throttle. The Tiger settles at 62 km/h, 38.5 mph, and the vibration disappears, smooth as glass. They hold that speed for 1 mile. The transmission temperature stabilizes at 82 degrees C. Fuel consumption is actually better than previous tests. Less power wasted means better efficiency. Wheeler brings the Tiger to a stop. Total test time, 4 minutes, 22 seconds. When Morrison climbs out of the hull, Baxter is waiting with a stopwatch and a calculator. 38.5 miles per hour. 10 miles faster than anything we've ever achieved, 15 miles faster than the German manual specifies. How? Morrison wipes transmission fluid from his hands. The German manual doesn't specify it. That's the wrong manual for this tank. This is an early production Tiger. It was designed to go faster. They just throttled it back in later models, probably for reliability or ease of training. But the original design, it's fast. How many tanks do the Germans have that can do this? Unclear. Maybe dozens of early Tigers, but here's the thing. We've been testing 131 with later spec parts for a year. We've been accidentally making it slower. The Germans, If they kept the original components, if they maintained their early Tigers properly, they've had this speed all along. The implication settles over the group. For 2 years, Allied intelligence has assumed Tigers top out at 28 mph. Tactics have been built on that assumption. Tank doctrine, infantry support coordination, artillery timing, everything assumes a Tiger can't move faster than 28 mph on roads. But they can. They always could. The test report lands on desks across British military intelligence on June 14th. The reaction is immediate and skeptical. This is impossible. Colonel Richard Pemberton, chief of the War Office's Tank Analysis Section, writes in a memo. The Tiger is known to be slow. Multiple sources confirm maximum speed of 25 to 28 mph. One test at an experimental facility, conducted under ideal conditions, does not override 2 years of combat intelligence. Baxter responds with data. Tiger 131 achieved 38.5 mph for sustained duration with no mechanical stress. This was not a momentary spike. The transmission operated normally. Temperature within acceptable range, no component failures. Request authorization for additional testing to verify findings. Permission comes through, but with conditions. The testing must be comprehensive. Different drivers, different track conditions, different fuel qualities. And most importantly, they need to test other Tigers. The problem is that Tiger 131 is their only runner. They have 2 other Tigers at Chobham, Tigers captured in Italy, but both have damaged engines. Morrison spends a week getting one operational Tiger 142, a late production model built in March 1943, June 23rd. They run identical tests on Tiger 142. Same track, same protocol, same measuring equipment. Tiger 142 tops out at 27.8 mph. This makes no sense, Wheeler says. Same tank, same engine, same transmission design. Why is 142 slower? Morrison already knows. He's examined both transmissions. 142 has the post-October 1942 modifications. Shorter pre-selector timing, different gear ratios optimized for reliability over performance. It's what the Germans decided was better for production tanks, more forgiving for average crews, less likely to break under abuse. So 131 is the exception? 131 is the prototype. Early Tigers were built to different standards. Higher performance, but probably harder to maintain, more demanding on crews. The Germans learned that combat tanks need to be soldier-proof, so they detuned later production models. The verification testing continues through late June. They run Tiger 131 30 times under varying conditions. Wet track surface, 36.2 mph, dry track. High temperature, 38.8 mph. Different fuel blend, 37.9 mph. Different driver, 38.1 mph. Towing, 2-ton load, 34.7 mph. The results are consistent. Tiger 131, when properly assembled to original specifications, is significantly faster than intelligence estimates. More importantly, it's faster than later production Tigers tested by Allied forces. But one question haunts the analysis. How many early Tigers remain in German service? British intelligence begins reviewing combat reports with new eyes. In Tunisia, before 131's capture, there were reports of unusually mobile Tigers during the Kasserine Pass battle. In Sicily, American units reported Tiger encounters where enemy heavy tanks achieved unexpected speed during repositioning. At Anzio, the German counteroffensive featured Tigers that moved with surprising rapidity. These reports were dismissed at the time. Battlefield observations are notoriously unreliable, colored by fear and chaos. But viewed through Morrison's findings, they form a pattern. The Germans had fast Tigers. Not all of them, maybe not even most of them, but enough to matter, and Allied forces didn't know. June 27, 1944. 3 weeks after D-Day, Allied forces are struggling in Normandy's Bocage country. The hedgerows, thick vegetation on earthen banks, create a maze of tiny fields and sunken lanes. Visibility is measured in yards. Tank engagements happen at point-blank range. Tigers are dominating. On June 13th, a single Tiger from Schwerpanzerabteilung 101 destroyed 14 British tanks near Villers-Bocage. The Tiger, commanded by SS Obersturmführer Michael Wittmann, appeared with shocking speed, hit British armor at close range where it couldn't maneuver, then withdrew before Allied forces could coordinate a response. The speed was unexpected. British tank commanders expected Tigers to be slow, especially in restricted terrain. They expected time to react, time to coordinate, time to flank. They didn't get it. More reports filter back. On June 26th, Tigers from the 2nd Panzer Division counterattacked near Shu, moving with uncharacteristic speed, according to British after-action reports. They hit Allied positions before artillery support could be properly coordinated. Baxter forwards Morrison's findings to Normandy Command with a warning. Early production Tigers demonstrate 35 to 40% greater speed than current intelligence estimates. Recommend immediate tactical revision. The response is mixed. Some commanders take it seriously and adjust tactics. Others dismiss it as laboratory conditions not applicable to combat. The problem is verification. How do you confirm a Tiger's speed when you're fighting it? On July 8th, Allied intelligence interrogates a captured Tiger crew from Schwer SS Panzerabteilung 101. The crew mentions that their Tiger, an early model built in August 1942, was known in their unit as Schnell, fast. They'd nicknamed it that because it could outrun later Tigers, sometimes by significant margins. How fast? The interrogator asks. Maybe 60-65 kilometers per hour on good roads, the driver says. Faster than the newer tanks. Our commander liked it because we could get into position quickly, hit them, then relocate before their artillery got us. 60 kilometers per hour, 37 miles per hour, exactly what Morrison found. The interrogation report reaches Chobham on July 12th. Baxter annotates it, confirms Morrison findings. Early Tigers demonstrably faster, combat crews aware and exploiting the capability. But by now, the Normandy campaign is evolving. Allied forces are adapting to Tiger tactics through hard experience rather than technical intelligence. They're learning that Tigers can appear quickly, that speed can't be assumed, that doctrine needs flexibility. Morrison's discovery matters, but its impact is dulled by battlefield reality. The war isn't waiting for technical reports. August 1944. With Normandy secure and Allied forces breaking out toward Paris, Chobham turns to a different question. Why did the Germans slow down their tanks? Morrison has been analyzing Tiger production records captured in Italy and France. The pattern is clear. Early Tigers, roughly serial numbers 25001 through 250100, had higher performance specifications. Starting around serial number 250122, October 1942, performance dropped, but reliability improved. The reason appears in a captured Henschel engineering memo dated September 15, 1942. Field reports indicate that Tiger Doi transmission failures correlate with operator experience. Experienced crews achieve satisfactory performance with current specifications. Inexperienced crews force transitions, overheat components, and experience premature failure. Recommendation: reduce performance specifications to increase tolerance for operational error. Sacrifice 10-15% speed for 40% improvement in mean time between failures. It's a rational decision. The Germans were scaling up Tiger production. They needed tanks that average crews could operate without destroying them. High performance is worthless if transmissions fail after 500 kilometers because the driver doesn't understand pre-selector timing. So they slowed the Tigers down. Not dramatically, 28 mph instead of 38 mph, but enough to make them more forgiving. The trade-off was worth it for mass production. But the early Tigers, the ones built before October 1942, those retained the original specifications. And some of them, maybe 30 or 40 tanks, survived into 1944 with original components. Morrison writes in his final report, German engineering philosophy differs fundamentally from Allied approach. We design for ease of manufacture and repair. They design for performance, then throttle back for reliability. Their best tanks are the earliest ones, before they learn to compromise. The insight goes beyond Tigers. British intelligence starts looking at other German equipment with new questions. Are captured examples representative? Did early production models have different capabilities? Has enemy equipment been underestimated because analysis focused on late production models? The answer repeatedly is yes. Early Panther tanks were faster than later ones. Early Bf-109 fighters had better power-to-weight ratios than late war models. Early U-boats had longer range than post-1943 boats. The Germans started with high-performance designs, then degraded them for production efficiency and reliability. Allied intelligence had been analyzing the wrong examples. September 15, 1944, Morrison is assigned to a new project, analyzing Tiger II tanks captured in France. The Tiger II, also called King Tiger or Royal Tiger, is the Tiger I's bigger, heavier successor. Allied intelligence expects it to be slower than the Tiger I. Morrison examines the first captured Tiger II and finds something familiar. Early production transmission components. Similar to Tiger I serial number 250031, he runs the same diagnostic procedures. Tiger II achieves 28 miles during testing, faster than the manual specifies, slower than it should be capable of. Same pattern, Morrison tells Baxter. Early production, high-performance components but assembled with later specifications. The Germans are making the same mistake we made with 131, mixing components from different production standards. He adjusts the Tiger II transmission to original specifications. On September 22nd, it achieves 34 mph, 6 miles faster than any Allied intelligence estimate. But the war is moving too fast now for technical reports to matter much. Allied tank crews are learning through experience, adapting tactics on the fly. Morrison's insights about German production philosophy are valuable, but they're not changing battles anymore. By October 1944, Morrison is back in Yorkshire, reassigned to industrial production. The war doesn't need diagnostic engineers anymore. It needs production volume. Tiger 131 remains at Chobham until war's end, then gets transferred to storage. In 1951, it goes to the Bovington Tank Museum, where it sits, static display, for decades. 1990, Bovington Tank Museum begins a restoration project. Tiger 131, the last running Tiger in existence, will be restored to operational condition. The restoration team faces the same question Morrison faced. How should they assemble the transmission? They have German manuals, but the manuals are contradictory. Early manuals specify different settings than later ones. Someone finds Morrison's 1944 test reports in the archives. The reports are detailed, technical, and specific. They describe exactly how to assemble an early production Tiger transmission for optimal performance. The restoration team follows Morrison's instructions precisely. In 1999, Tiger 131 runs again for the first time in 47 years. During initial testing, the Tiger achieves 38 mph, exactly what Morrison measured in 1944. It's remarkable, the chief restoration engineer says in a 2003 interview. Morrison's work was essentially forgotten for 50 years. Everyone assumed Tigers topped out at 28 mph because that's what the manual said. But Morrison proved the manual was wrong, or rather it was right for the wrong tank. Early Tigers were genuinely faster, and the Germans knew it. Modern analysis of German combat records confirms this. Units equipped with early production Tigers consistently achieved higher movement rates than those with late production tanks. The difference wasn't huge, maybe 10–15%, but in combat, that margin could be decisive. At Villers-Bocage, Michael Whitman's Tiger was serial number 2501-P2, an early production model. Its speed allowed the rapid attack that destroyed 14 British tanks in 15 minutes. A slower Tiger might not have achieved the same result. At Anzio, the Tigers that American forces reported as surprisingly rapid were from Schwerpanzerabteilung 508, equipped primarily with early production tanks. The pattern repeats across combat records. When Germans had fast Tigers and used them aggressively, they achieved outsized results. When Allied forces assumed all Tigers were slow and got caught by fast ones, casualties spiked. Morrison's 1944 discovery didn't change those battles. Most happened before his testing was complete. But his insight about German production philosophy, about the difference between early and late examples, that changed how intelligence analyzed enemy equipment for the rest of the war and beyond. Alan Morrison never became famous. His contribution was too technical, too specialized, too buried in classified reports to generate publicity. After the war, he returned to civilian engineering, eventually becoming chief engineer at a mining equipment firm in Wales. He retired in 1975 and died in 1983, largely unrecognized, but his test reports survive. They're in the UK National Archives, hundreds of pages of technical analysis, oscilloscope traces, component measurements, and engineering insights. The reports are remarkably detailed. Morrison documented everything, including failed hypotheses and dead ends. In 2008, a researcher studying Allied tank testing finds Morrison's reports and realizes their significance. The researcher, Dr. Thomas Jentz, publishes an analysis. The Morrison Tests, Allied Understanding of Tiger Performance, 1944-1945. Jentz's work reveals something else. Morrison tested more than just Tigers. Between June and October 1944, he analyzed transmissions from Panthers, Ferdinands, Jagdtigers, every German heavy vehicle Chobham could acquire. In each case, he found the same pattern. Early production models were faster and more powerful than late production models, but Allied intelligence used late production manuals to assess early production equipment. Morrison's insight was simple but profound, Jentz writes. Equipment capabilities change over production runs. The enemy's best tanks might be the old ones, not the new ones. Intelligence analysis must account for production variants, not just model types. This seems obvious in retrospect, but in 1944 it was revolutionary. Allied intelligence had been treating each tank model as monolithic. All Tiger-Is are the same, all Panthers are the same. Morrison proved that production variants mattered as much as model variants. Modern military intelligence now routinely tracks production changes in enemy equipment. When analyzing Russian T-90 tanks or Chinese Type 99s, analysts compare early to late production, looking for performance differences. It's standard procedure. That procedure traces back to Morrison's 1944 testing at Chobham. Today, Tiger 131 still runs at Bovington. A few times each year, the museum demonstrates it for the public. The Tiger rolls onto a concrete pad, engine roaring, tracks clanking, exactly as it did in 1943. The demonstration never exceeds 15 NP, insurance and safety restrictions. But the restoration team knows what the Tiger can do. During closed testing, away from public view, they've verified Morrison's findings. 38 mph, sustained, no mechanical stress. It's extraordinary how wrong our assumptions were, the current chief engineer says. For 50 years, everyone thought Tigers were slow because that's what captured manuals said. But the manuals were describing simplified mass production versions. The original Tigers, the ones German engineers designed before they had to compromise for production, those were fast. How fast? Faster than a Sherman, faster than a Cromwell, fast enough to control engagement timing, to choose when and where to fight, to appear with surprising speed and withdraw before Allied forces could react. That speed was always there. German crews knew it. Some Allied tankers learned it through hard experience. But Allied intelligence didn't know it, not officially, not in doctrine, until Morrison proved it in June 1944. By then, the fastest Tigers were mostly destroyed or worn out. The war was too far advanced for technical insights to shift its course. Morrison's discovery came too late to save the lives it might have saved with earlier warning. But it taught a lesson that outlasted the war. Question the manuals. Test the assumptions. The enemy's best weapon might not be the new one. It might be the old one, the prototype, the early production model that got quietly downgraded before mass production. The Tiger that roars at 38 miles per hour isn't the Tiger Allied intelligence prepared for in 1944. It's the Tiger the Germans built in 1942, before they learned that perfection doesn't scale, before they compromised performance for reliability. It's the Tiger that Alan Morrison, a civilian mining engineer who knew nothing about tanks, discovered in a Surrey workshop by listening to harmonics in a transmission and refusing to accept that the manual was always right. It's the Tiger that shouldn't exist, according to every intelligence estimate. But it did exist. It still exists, and once a month at Bovington, when the museum runs Tiger 131 in private testing, it still achieves 38 miles per hour. The speed the Germans never officially acknowledged. The speed Allied intelligence didn't believe. The speed one engineer found by rebuilding a transmission and trusting his ears more than the manual. The speed that changed nothing, because the war moved faster than technical reports. The speed that changed everything, because it taught military intelligence to question what captured documents say and test what the enemy's best equipment can actually do. Somewhere in the UK National Archives, Morrison's June 12, 1944 test report still exists. On page 47 in precise engineering handwriting, Morrison wrote, "Maximum sustained speed, 62 km/h, 38.5 IDH. Recommendation: revise intelligence estimates immediately. Early production Tigers significantly more mobile than current doctrine assumes." The recommendation went unheeded until it didn't matter, but the insight that the enemy's actual capabilities might differ from captured specifications, that insight became doctrine. Alan Morrison rebuilt a Tiger's transmission and unlocked a speed no German manual listed. In doing so, he revealed a principle that military intelligence still follows. The manual tells you what the equipment should do. Testing tells you what it can do, and sometimes what it can do is far more dangerous than anyone expected.